Hi, I'm Yuejie, and in this video I will be presenting ConfMask, enabling privacy-preserving configuration sharing via anonymization. This is a joint work with Menqiu Tong, Xiao Yao, Chen Yongting, and Liu Guyue. Configuration sharing is needed in various scenarios. When there is a network outage, the administrators sometimes need to collaborate with technicians outside of their institution, such as posting their questions on online forums or outsourcing their management tasks to a third party. Another example is academia needs network configurations as research data. For instance, for recent LLM-based research in networking, real-world configurations are a valuable source of input to enhance their performance. Other types of research, such as network analysis, also benefit from public configuration data. But real network configurations are hard to obtain for academia. For example, the Internet Topology Zoo only provides a database of network topologies without the corresponding router configurations. Other synthetic tools, such as NetComplete, provide auto-generated configurations from input topology and route specifications, but their output lacks diversity in protocols and vendors. So public network configurations are mostly incomplete or unrealistic for research purposes. On the other hand, real and complete configurations are rarely shared by the enterprise because sharing the full network configurations raises privacy concerns. So on the online forums, we usually see only parts of the full configurations that hopefully solves the given issue. This could lead to inefficient communication between the owner of the network and the outside technician. We notice many cases where it takes multiple rounds of clarification before the task is solved. So we think the pain point for the industry is collaborative debugging using online forums is inefficient, mainly due to privacy concerns in the configuration sharing. Both the industry and the academia need a way to share the configuration of a production network without compromising the privacy of its owner. Our intuition is to use anonymization to solve this problem. Specifically, our solution needs to anonymize the configuration files for privacy concerns while preserving their utility for various use cases at the same time. In this talk, I will first introduce the background of network anonymization. Then I will explain the challenges and propose the key ideas of ConfMask. After that, I will go through the implementation and the evaluation results. And lastly, I will discuss some limitations and future works. Now, for the background of network anonymization. Existing approach is mainly focused on substituting sensitive data, such as usernames. A few algorithms, such as NetConan, propose prefix-preserving IP substitution, so the subnet relations can be preserved after anonymization. But we notice that some implicit sensitive data can be inferred from the configuration files, which are not anonymized by any of the existing algorithms. Inferring the topology or data plane from the network configuration is quite simple. Like we have network simulation tools available with high fidelity and scalability. These types of implicit information are critical to the privacy of the network owners. For example, the topology might imply the scale and the structure, and the data plane might expose communication patterns and relations of departments in an enterprise. So we need a systematic approach to anonymize implicit sensitive data in the network configurations. There are several existing approaches that can anonymize network topology or data plane separately. When the topology is viewed as a simple graph, existing graph anonymization algorithms can provide anonymity in properties such as node degrees and node identity. However, they are originally designed for social networks and cannot directly apply to configuration files. For the data plane, a previous work called NetHide provides an obfuscation method for software-defined networks against link flooding attacks. But SDNs are much more flexible and programmable than traditional networks such as Cisco routers. And the root cause of some issues becomes hidden after NetHide obfuscation, which means this approach does not always apply to troubleshooting scenarios. In summary, ConfMask aims to protect the privacy of network owner during configuration sharing. Specifically, ConfMask modifies the configuration files such that the network topology and data plane appear to satisfy certain anonymity properties under network simulation. During this process, ConfMask also guarantees the utility for our target scenarios, including troubleshooting and research tasks. Let me first introduce some notations and terminologies used for the rest of this talk. The configuration files are denoted as CFG, which consists of two implicit privacy properties. The topology is represented by a simple graph G, which is constructed from the routers and the links in the configurations. The data plane DP is defined as end-to-end routing paths in the network, and we specifically consider the hosts as routing destinations. The anonymized configurations, topology, and data plane are denoted by the same notations with a subscript A. So now we can declare our desired anonymity and utility properties. For the anonymity of topology, we target the node degrees in the graph G. And for the data plane, we anonymize the routes between each pair of edge routers, which are the routers directly connected with end hosts. For our utility goals, we require that the original topology must be a subgraph of the topology after anonymization. For the data plane, we require all host-to-host paths in the original data plane to exist in the anonymized data plane. We call these utility properties functional equivalence, denoted by FE. For the formal definitions and theoretical proofs, I recommend referring to our full paper for details. Next, I will explain the challenges and our insights to solve them, and I will propose the key ideas of ConfMask. We summarized 3 key challenges in achieving the anonymity and utility requirements. First, we deal with multiple privacy properties at the same time, namely the topology and routing paths. They are implicit information, and they are tightly coupled in the configurations. It is challenging to ensure their consistency and prevent straightforward de-anonymization. The second challenge is controlling the routing behavior to preserve the complex routing utility, especially when multiple protocols are configured in one network. Lastly, we need to consider the complexity of our workflow so that it is scalable to large networks in production. To address the first challenge, we notice this dependency ordering. We say that two properties, Y is dependent on X. If modifying X inevitably impacts Y, but we might find a way to modify Y without affecting X. We find that first, the construction of the data plane is dependent on topology changes, and second, at a higher level, achieving an anonymity requirement is dependent on preserving the utility in advance. This ordering determines the high-level workflow of ConfMask, which I will soon introduce. For the second challenge, the utility guarantee of the topology is relatively easy to verify, while the data plane is much more complicated. We utilize network simulation tools for data plane verification so that we can iteratively make incremental changes to the configurations until the routing utility is preserved eventually. Following the second insight, there is a scalability challenge because of the trade-off between security and computational complexity. We reduce complexity by using local forwarding table information to modify the configurations. Here's an overview of the ConfMask workflow. Following our first insight, we designed 2 major steps to deal with topology and data plane in a sequential way. At the beginning of our workflow, we take the original configuration files and simulate the original topology and data plane as baselines. In step 1, we focus on anonymizing the original configurations to generate anonymized topology while preserving the utility. We use a running example to explain each step. On the left side is a part of the original topology, which is viewed as a simple graph. We first choose a graph anonymization algorithm that only adds edges to the graph. This will ensure the topology utility preservation. On the right side is the corresponding topology in the anonymized network. The dashed lines denote the edges to add in our chosen algorithm, which guarantees k anonymity for node degrees. Then we add the corresponding link configurations to implement the same algorithm in configured files. After dealing with the topology, when we look at the route from host 1 to host 5, as expected, the data plane is affected by the topology changes. So we revisit our high-level workflow and break down step 2 into 2 smaller steps. First, on top of the new topology, we need to restore the utility properties according to the original data plane. Recall that the data plane utility is defined as the set of host-to-host paths. We take the intermediate configuration output from step 1 and simulate the paths in the current data plane. Next, we compare them with the original set of routing paths, and we should expect to find some routing paths that are not preserved. So we add new configuration lines to modify the routing behavior. Based on our second insight, at a high level, we only need to repeat this loop of simulation, comparison, and modification iteratively until the data plane is restored. But how do we control the routing behavior and guarantee that it can be eventually restored? We first thought of two straightforward strawman solutions to do this. As the routing difference are brought by the fake links we add in step 1, a static approach is to configure the fake links such that they're always least preferred and never used for routing. Although this approach guarantees to terminate in just one iteration, the security disadvantage is obvious. By simulating the data plane and removing links without any traffic, the topology is easily de-anonymized. So we thought of the second strawman approach that corrects each hop of each path individually. We can simulate trace route queries and only reconfigure the wrong next hops for the destination network of each path. In our running example, in iteration 1, we impact the host 1 to host 5 route by blocking the link between router 1 and 5. And for iteration 2, we do another trace route and see that the link between router 2 and 5 needs to be blocked. And we need one more iteration to block the link between router 2 and 4. Now the original route is restored. This approach is much harder to de-anonymize, but we can see that the computation complexity is too high to scale to large networks. So here comes the third challenge of ConfMask. We need to strike a balance between the security of the output configurations and the computation complexity. We solve this by finding a set of conditions we call strong functional equivalence, which we design separately for different types of protocols. The significance of the SFE conditions are satisfying these conditions will be sufficient to guarantee the utility of the data plane, and they are easy to verify with only local information from forwarding tables. We use a distance vector protocol as an example to show how these conditions accelerate ConfMask. We look at the forwarding table entries of destination host 5 in every router and find that the FIB entries in router 1 and 2 are different from the original. So we modify the configurations for both of these links in one iteration, and for the next iteration, we find that only router 2 contains a wrong FIB entry. After fixing that, the original routing path is already successfully restored. Using SFE conditions for restoring data plane utility accelerates each iteration with a much smaller FIB lookup scale and also reduces the number of iterations. Now that the utility is preserved for the data plane, the next and final step is the data plane anonymization. As we choose the host IPs as routing destinations, we replicate each host k times on the same edge router, only substituting with fake IPs. Then we add random filters on these fake destinations to create distinct paths between each pair of edge routers without affecting the utility we just restored, and achieve an upper bound of k-anonymity for the data plane. We implement ConfMask in Python and use Batfish as the network simulator in the workflow. Next, I will go through the evaluations of ConfMask. We anonymize 8 networks of various routing protocols and scales as listed in the table to evaluate ConfMask from 3 different aspects, including anonymity, utility, and scalability. The first figure shows that ConfMask successfully achieves the theoretical topology anonymity guarantee provided by the algorithm. And the second figure shows that under our evaluation setup, ConfMask achieves an average of 96.5% of the expected route anonymity. Our evaluation also confirms that ConfMask can 100% preserve the utility properties we defined. Compared with previous approaches on data plane obfuscation, we believe ConfMask significantly improves the usability of the anonymized configurations. For the scalability of ConfMask, we compare it with the strawman solutions we propose. The execution time of ConfMask is acceptable. As expected, it is slower than the first strawman solution, which guarantees to terminate in one iteration, but severely compromises the security. And it is much faster than the second strawman solution, which for most of our evaluation networks does not terminate within a reasonable time. Lastly, I will discuss some limitations and future works. There are a few straightforward directions to extend this work. In ConfMask, we only focus on the privacy of the implicit information included in the configurations, which is orthogonal to substitution-based approaches. For example, netcode can be appended to ConfMask workflow to further hide the network address. Another way is to use different graph anonymization algorithms to satisfy different anonymity requirements. The same workflow will apply to any algorithm that only requires edge additions. And of course, we acknowledge several limitations in the current workflow. For simplicity, ConfMask uses host IPs as destination networks. So to support other routing destinations such as internet hosts, the IPN subnet management will require a more general design. Another limitation is ConfMask is only compatible with edge addition graph algorithms, which means the network scale is not anonymized. And lastly, as more routers will enable SDN in the future, how to extend ConfMask to support SDN is also an interesting question. In conclusion, the industry and academia could benefit a lot from sharing network configurations, but first, we need to remove the privacy concerns. Anonymization is commonly used for privacy preservation, but we notice many implicit privacy properties included in the configurations, which existing works fail to consider. In ConfMask, we propose an anonymization workflow focusing on the implicit sensitive data, including the topology and data plane. And ConfMask generates anonymized configurations that achieve both privacy and utility properties. ConfMask is now open source on GitHub in the link below. Thank you for watching.